All right, here's a few news articles you might like. While we're waiting for the official start of class, there's an incident response contest. Sort of like a CCSF. It sounds pretty good. You win a $5,000 vacation. If you win, it's the IR challenge, and it starts on May 15. And then they're going to send you some information, and you have to figure out something about who attacked them and how they attacked. So it's going to, the example task gives you someone who notes file movement and illogical date tampering on a desktop, and you have to examine it and find the source of the anomaly, and it challenges you with more and more challenges. So it sounds pretty good. Might be a good thing to do. All right, there's lots and lots of coronavirus stuff happening. This guy is Texas's lieutenant governor, and he said they need to open up the state because there are more important things than living, which I think is a very classic American attitude. I think a lot of countries in Europe don't understand this, and I don't think I do either, because I come from California, and San Francisco is pretty much more like living in Europe than America. It seems to me like the whole point of things is the people, but it is a classic American position that making money might be more important than the people. Although, of course, there's perhaps some logic saying if you lock the people up and you do not provide any money for them, and they have no money, so they become desperate, then you're hurting them too. And that is sort of what we're doing. Anyway, here's Katie Mazuris, who made Microsoft's bug bounty program, and I think she was also important in getting the Department of Defense bug bounty program. And she's pointing out the flaws in these bug bounty programs. And the way they work is when you sign up for the bug bounty program, the first thing they make you do is sign a non-disclosure agreement saying you will never tell anybody what you find. And then they'll decide, when you tell them, that they aren't going to fix it and they don't care and it's out of scope, and yet you're still bound to never tell anybody. So the main benefit that companies get out of it is that they get to hide bugs forever, which is what most companies want. That's what Microsoft's official position was for years, is we don't have to fix anything, just shut up and nobody will find it. And, you know, so hopefully we can get past that. That is a step. First, you try to deny there are any problems at all. Then you just try to cover it up. And eventually you have to admit you have problems. And then you have to budget an ongoing expense of constantly fixing problems and taking bug reports and stuff. And of course, nobody likes that. And nobody does it easily. They get forced into it by a gradual process of being humiliated. Anyway, so B-Sides Las Vegas is canceled. And it seems very clear they're going to have to cancel DEF CON and Black Hat 2. Dark Tangent was going to wait until June 1 to announce the fate of DEF CON, but now he's moved that into May 15. It seems increasingly clear that we can't do this, although, as you probably know, an increasing number of red states are going to just open anyway and totally ignore this. And Georgia is the one that's going to open this Friday. It's going to open for all kinds of normal business and just pretend everything is fine, which is an interesting technique. And it's an interesting social engineering experiment, because certainly what will happen is that 3 weeks later, a bunch of people will be dying, but they will then perhaps be able to distract people and pretend it's due to something else and just carry on. We'll see what happens. But the red states are opening up. And so Barr, the Attorney General, I think, has now said he's going to sue states who have too much stay-at-home orders. And that would go along with what Trump tweeted a couple of days ago when he said they should just liberate the states. But I just saw in the news, Trump just said, oh, they shouldn't have opened up Georgia. So Trump's trying very hard to contradict himself more often than usual and make sure he's on both sides of this so he can claim that whatever good that happens, it was his idea, and whatever bad that happens, he said not to do that. And that might work. His supporters seem to love this. And they love him as much as ever. So I don't think they're bothered by this at all. I was doing a news article yesterday, the day before. It reminded me of the Jehovah's Witnesses, where they predict the end of the world every year or two. And then when the world doesn't end, they just predict the end of the world again. And their followers just go along with it. It's like exciting and fun. True believers will never leave just because of contradictions. Anyway, the US Congress cannot vote except by being in person. And this is a big problem. The House of Commons in Britain has arranged to vote using Zoom, same thing we're using now, which is perhaps not a wise idea since Zoom is not very secure, but anyway, that's what they're going to do. The US Congress is trying to work out the same thing, but the Republicans are opposing it the same way they opposed letting people vote by mail in Wisconsin, because the Republicans at least Trump believes, although some other Republicans don't agree, that they must prevent people from voting. That the more they prevent people from voting, the more they will favor Republicans. That is not entirely clear. There are an awful lot of old, sick Republicans that would like to vote by mail too. So it might not be as much to their advantage as they think, just to blindly suppress a vote everywhere. Anyway, I think that's enough of that. We'll get on to the official class stuff, which is here. And I did make some changes. The main change I made is one I'm sort of reluctant to do. However, when you look at the projects, it is clear that a lot of students can't do the iPhone projects. I mean, you can do the iPhone projects, you need to have a phone and you need to have a Mac. And a lot of students don't. And now the physical labs are shut down. I can't really loan what I can to students. And so I made this stuff all extra credit, which means, you know, this class will be a lot easier. This will be good for people who are behind. It'll be easier to catch up. I've decreased the number of required projects. So this is all extra credit. You have until the last day of class to do them. And if you don't do them, it doesn't matter, because it's really unreasonable for me to require any iPhone projects under the current condition of everybody being locked down. So I calculated the new point total and how many points it takes to get various grades, and you'll see it in Canvas in an announcement. So it should be easier for people to achieve that total. There's less total hands-on, so that creates a schedule which is a lot different than what I usually do when you have 1 or 2 projects due every week. Now, all the required projects have been due weeks ago, and all there's left is extra credit for the rest of the class. So anyway, because remember, I made a decision at the beginning of this semester to focus more than usual on iPhone, and then, because of this disaster, my ability to distribute the necessary hardware to people went down. So anyway, this class will get easier, although you still have the projects to do if you can get your hands on the equipment. Anyway, all right. So that's the situation. You should all just be doing extra credit projects or try to catch up on old projects if you like. That's quiz 2A, not 2AE. Anyway, I have put up quiz 3A today, and I'll put up quiz 3B by next week, and that'll be the last quiz. And we will cover chapter 3. And okay, if you got any questions about the scheduling or anything, let me know. If you need more time on things, let me know. If you need incomplete to give you a whole extra semester to finish, let me know. All these things are possible. And another thing is, if you're desperate for extra credit, you could do COBOL CTF, which is down here someplace. There it is. You can do the COBOL CTF. We're doing this. This is a surprisingly big hit considering how crazy it is. And just get your points on the scoreboard and email it in and tell us who you are. And you can get some extra credit that way too, if you're in need of points. Anyway, I got my chat message open, so I see nobody is asking questions. Let me make sure I really started the recording. Good, all right. So let's take a look at the slides for this iPhone stuff. So let me make this bigger yet. All right. How about this? There we go. All right. So this is analyzing iOS apps, and we're going to do the second part. So it's going to be the data protection API, the keychain. Oh, I have to move this closer. Touch ID and reverse engineering binaries. All right. So the Apple system is very complicated with many layers of encryption, far more complicated than Android, as we're going to see, but you can still mess up. So City Mobile, 10 years ago, saved user information in a hidden file, but that hidden file was apparently not encrypted, not protected correctly, so your data could be stolen out of it. And as we've seen, a lot of Android apps make similar mistakes. But there's a lot of encryption in modern versions of iOS, and even going back several years. There's an encryption key for each file there, and there's these protection classes, and there's the secure enclave in iPhones, which is the special cryptographic coprocessor. So it has a device encryption key in that device that cannot be accessed by the processor at all. So that is pretty good. And then you've got a passcode key. When you type in your passcode, it uses PBKDF2 to create a encryption key. And PBKDF2 is just the same thing used to hash passwords on Linux. It's many rounds of SHA-512 or something to make a long cryptographic key. And so you have a UID key, That's unique to your device, and it's stored in the hardware-based crypto accelerator called the Secure Enclave, so it cannot be accessed by any software. Even if you root the device, you can't find that key. And so when you boot up the machine, it takes the UID key, and then it creates a device key from it, and then it's able to boot up the operating system. And so the files that have no protection at all can be accessed with those keys. But all the other files with higher levels of protection require the passcode key. So for example, if you jailbreak your device with CheckRain and get access to the system files, you only have these files. You can't get these files because you don't have the user's passcode, which is why I say CheckRain is useful for studying iOS internals and understanding how it works and finding bugs in the iOS files, but it is not useful for stealing personal data from a stolen iPhone. It won't get you there because of this passcode here, and that's why the FBI got so mad. Even if they take a phone at a crime scene and they manage to get past the boot up sequence here with a jailbreak exploit, they still can't find the personal files like emails and instant messages and stuff that they want without the passcode, and even Apple can't get past that. So once you put in the passcode, now you create a passcode key with PDKDF2, and these two keys are used together, these three keys, for various levels of encryption. And here, most people don't shut off their phone all the time, of course. They just put it in standby, put it in their pocket, and then they pull it out again. So there's an intermediate level of file protection here, which is protection until first user authentication. So if you have already put in your passcode and just put it to sleep, then these are available. And so a phone you find at a crime scene, I think you might reasonably expect to get these because it probably isn't turned off. It's probably just asleep. But we'll look at more later. I'm not sure if putting it to sleep blocks this stuff or not. But anyway, here's one where you actually have to have your passcode to get to it. But I think that's the point of this. You have not totally turned it off since the last time you authenticated. Now, the point of that is, if you wanted to jailbreak the phone, you typically have to reboot it entirely. So the point is you have the phone and these files would be available, but you can't get in because you don't have the passcode and you don't have the UID key. And so you can't get them even by coming through the system, not without rebooting the phone to jailbreak it. And when you reboot it, these will be locked, waiting for the passcode. So that's why this protection class does make sense. So that's the game. No protection. Complete protection is inaccessible when devices are locked, and complete unless open means when the device is, if the file is in use, it's unencrypted when the device is locked. So anyway, then there's this one, from boot up to first unlock. This only protects it from attacks requiring a device reboot. So you have various levels of these encryption protections available. Now you have the keychain. Remember, there's a similar thing in Android. There's a similar thing in OS 10. What I guess it's called Mac OS now on your desktop. There's an Apple keychain to store secrets. This is not necessarily in the SE chip, but it is a secure place to put things. And so you have many protection classes in the keychain. Some you can make things always accessible only when the device is unlocked, after the first unlock from boot, just like the other ones. And there are some others. Cannot be migrated to another device, and so on. And here you can only have these things stored when you have a passcode on the device. If you've been doing the Android projects, you probably noticed this. If you want to put a custom HTTPS certificate on an Android phone, it has to be, I think, Android 7 or earlier, then you can do that, but you can only do it after you put a passcode on the device. It won't let you do it before that. And that's what you'll be able to do with this parameter. On iOS, you'll be able to set certain things which can only be done on phones with a passcode. All right. So you've got authentication policies available in iOS 8, and these will prevent access to the items when there's no passcode. And in order to get in, you'll have to put in the passcode or a fingerprint. Although I'm imagining, and my phone uses Face ID, and that's after your textbook, so it's not covered here, but I imagine it works pretty much the same as Touch ID. So you can run Keychain Dumper. That will dump out the contents of the keychain as whatever portions of it you are entitled to get to. And then there's Touch ID. If Touch ID is not enabled, then Secure Enclave holds the data protection class keys. And when it's when you lock the device, it throws them away and those keys are gone. So that's the complete protection class. But if you have Touch ID, then it has to use a key derived from your passcode, even though you're not entering your passcode. Now, this is a sort of difficult logical problem, and both Apple and Microsoft messed up very badly when they first started implementing USB thumbprint readers for this issue, because you are putting in something that is not your password, and yet you really need your password. So one solution is to store your password somewhere, and that kind of undoes the whole point of the secure enclave. So this is what Apple did. The key is held in memory, but it's wrapped with another key. And Touch ID authentication gives you the unwrapping key. So this is a better solution. You have layers of encryption. And as long as this key encryption is strong enough, then you're still as strong as ever. This reminds me of what Cloudflare did. When Cloudflare wanted to provide their service to banks, they had a problem because they wanted to man in the middle HTTPS connections, which is in principle impossible, but the banks are all secure and you don't want to give you their private key, which is what you need. So what they did was they created layers of encryption, sort of like a VPN, where it would add some other encryption from point-to-point traffic to get to the bank, so they could still handle a lot of the traffic locally and still maintain security all the way. But it wasn't exactly the same kind of encryption all the way. The same thing happens with encrypted email. It's not just one point-to-point encryption all the way to the end. And for that matter, Zoom is the same. It's not end-to-end encrypted, which means I'm talking to you now and you people have joined the session. And what some people would like is to say that you would have a key and I would have a key, and the key would be only at the endpoints. So nobody in the middle could read anything. But that's not how Zoom works at all. I'm connected to their server with HTTPS, and they have the key. They then decrypt the stuff and re-encrypt it and pass it down to all of you over HTTPS. And that is not the same. In principle, there's a person in the middle, and Zoom says this way they can block offensive content and such. I mean, anyway, email is encrypted hop to hop, but in between decrypted. Anyway, does Tor work something like that? The point of Tor is to be super private. So Tor does the opposite. Tor, every time you a relay picks up Tor traffic and forwards it, it re-encrypts it with more encryption. So you send something through an entrance relay, and by the way, it doesn't have to be encrypted in the first place, although that would be good. You could send it over HTTP or FTP, and then that encrypts it and passes it on, and that encapsulates and encrypts it again and passes it on, and encrypts it again and passes it on. And the reason it does that is that means none of the devices in the middle can see what they're sending, and they also do not know where it came from. So and the point is both to maintain maximum security and also to obtain legal deniability, because I did this. If you open up a Tor relay and start donating bandwidth and processing power to the Tor network, you are handling the most horrible stuff in the world. You are handling software piracy, kiddie porn, malware, all the most rotten stuff in the world is going over Tor. That's what most of the traffic is. So you don't want to be legally liable for what that stuff is. So you would like it to all be encrypted so you can say, I don't even know what's there. Anyway, I only ran mine for a few days before I got the flood of complaints, and I said, I'm not really happy with this, and I took it down like MIT did. But anyway, Tor does the opposite. Instead of encrypting point-to-point and having clear text at every endpoint, which is the way encrypted email works, it has many layers of encryption, so it simulates point-to-point encryption. The problem is with Tor is if you own most of the nodes, then you can actually reverse engineer it. And the Department of Defense, the American government, has most of the nodes. This is the sort of open secret of Tor. The US government can, in principle, reverse it in practice, but it's expensive. And so it serves the civil libertarians like the EFF explain this. Your point of using high encryption is not to hide things perfectly from the government, because that's impossible. They could just stick a bug in your house, stick a camera in your house. I mean, there's a way to find secrets. What you're doing is just making it more expensive. So they can't just sweep up all the email in the world and store it in Utah and then hunt through it later for whatever they decide to call illegal later, which is what they're worried about, because that's what J. Edgar Hoover did. He had these records of everybody. He knew everybody's secrets, and he would use it to blackmail people into doing what he wanted in Congress and other government positions. He knew everybody's drug addiction and sexual improprieties and everything else. And we don't really want a scary spider like that at the top of government operating in secret. So what we'd like is to have the Fourth Amendment, where people have to have probable cause to believe you're doing something bad, signed by a judge before they intercept and read your traffic. And that's what end-to-end encryption would tend to favor. Anyway, so it's a very timely issue. So anyway, Chaos Computer Club broke Apple's Touch ID. Yeah, Hoover wore spiked heels. Yes, there's persistent rumors that Hoover himself had his own sexual secrets, which would make sense. Anyway, so Chaos Computer Club in Germany, they broke Apple Touch ID back in 2013. They found what anybody could have told you, which is you're leaving your fingerprint everywhere. So it's probably pretty easy to get your fingerprint and then make a fake thumb that will fool the fingerprint biometrics, and they were able to do that. And I think the same thing's true of facial ID, which I use on my phone. A lot of people do, but I'm aware it's not very secure. You could probably just take a photograph of my face or anything else and pretty easily fool it. These days, I have another problem. My phone uses Face ID, and every time I'm shopping, I'm wearing a mask these days, so it doesn't recognize my face. So I have to put in, so far, I've accepted typing in the passcode all the time to make purchases of my iPhone, but the alternative would be to retrain it to recognize my face with a mask on. I'm not quite sure if that's the right move, but that might be the move if this goes on much longer. And it looks like this lockdown is going to go on for a lot longer. Anyway, all right, so iOS binaries are here. We've been through reverse engineering Android files, which are written in Java and they run in Smalley in a Java virtual machine. So the code that actually runs is pretty easy to read and modify. However, iOS binaries are not that way. They are compiled down to real ARM assembly code, just ARM binaries, just like x86 and x64 are compiled down to real binaries. So the process is more like the real reverse engineering at the binary level that we're doing in the 127 class. They're called Mach-O binaries. In Linux, the files are called ELF. In Windows, they are called PE files. And on iOS, they are called Mach-O. These are just different ways to set up binary executable code and all the variables and metadata that you need. So there's three parts to it: header, load commands, and data. And so it looks like this. You've got a header to start it off. You've got a region of load commands, and then you have data sections, which these load commands refer to. If you've been taking 127, this is pretty much like the PE format, where you have these various segments, and up in the start, you've got an import and export table and so on. Your load command tells it where the symbols are, which would be named variables and such, what sections are encrypted, what libraries to import and where they are, and that sort of thing. So on top of that, you have multiple executable files in the same package. You don't always have them, but you commonly have them, because if you want to put an app in the App Store, you would like everybody to be able to use your app. And some of those people have old phones and some of them have new phones. Now, in the world of Windows, Microsoft addresses this by making every version of Windows backwards compatible. So you can write code written for Windows 95 on Windows 10. And Windows XP and everything, and that is a big burden, and that's part of why Windows keeps getting bigger and bigger and bigger and more bloated. Apple does not do that, most emphatically. Apple's opinion is that if you have anything that is 2 versions back, they don't support it, you should throw it away and buy a new device. They don't care. They do not maintain backward compatibility at all. So for iPhones, you do it this way. You make a fat executable that has several different versions of your app compiled for different hardware in there. So you can have ARM7, ARM64, ARM7S, and those are for all the different versions of iPhones and iPads and iPods and so on. So if you are just a sort of amateur, you might make an app that only runs on one generation of phones. But if you're a professional app making like the Safeway app and you want everybody to get it, then your app will be big and fat and have several of these things inside there. That's called a fat binary. OTool is one of the command line tools that can see this. So here you have on OTool on this app. And OTool tells you that it has 2 different CPUs. It has CPU type 12 and CPU type 16777. And if you look back here, 12, those numbers, it's here. 12 is ARM6 and 16777 is ARM64. I don't know why they didn't just make it 13 or something, but anyway, that's what they did. The 64-bit has that long number. So This thing is compiled for both 32-bit and 64-bit hardware, which is pretty nice from a viewpoint of being able to distribute the app and have more customers use it. All right, LiPo is the tool you can use to extract one of the executables from a fat binary. So this would take out just the ARM7 version from the file, and that is something you might do if you want to reverse engineer it, because your reverse engineering tools like Hopper can you only reverse engineer one binary at a time. So you'd have to break it up into individual binaries to do further inspection. All right, and then there's the security features. Pi is the all-important feature for address space layout randomization. As we've been going through in 127, if you do buffer overflows, you have to jump to code you've injected and you need to know where it is. So to prevent people from doing that, you randomize the location of code in memory, but that means you have to compile apps to not use any absolute addresses inside the app. It has to be all portable, so it can all be relocated in memory and the app will still run. So that's called Position-Indendent Executable code, and it's a command line switch when you compile apps, although nowadays it's the default in most compilers. So all built-in Apple apps have it, but other apps might not have it. If they were written with an old version of, or with unusual command line switches when compiling, some apps might be old and not have this ability, and then that app cannot be randomized in memory. This is how you overcome this defense. We're doing it a lot in 127. It turns out that no current system actually randomizes everything. There are some parts of the operating system and some apps that are not randomized, so you can still exploit it by finding the code that is not moving around. Anyway, stack smashing prevents buffer overflows where you have a string variable and you reserve room for maybe 10 characters, but you put in 100 characters, so it overwrites data beyond where the area that was reserved, and you eventually hit a return pointer, which you can use to control the execution. So to prevent that, you put a canary value. The operating system puts a canary value at the end of the stack. So if that value has been modified, it knows a buffer overflow has occurred and stops the execution, so you don't get a chance to take over the phone. The LLVM compiler can do this, and just like the Windows compiler that we're using in 127, it is smart, and it does not always put the canary there. In order to maximize the speed of your app, it doesn't bother putting this defense on subroutines that don't appear to need it. So it picks functions that need it, and typically these are ones that use character arrays. So just like in the Windows compiler for Microsoft, this is enabled by default for all modern apps. All right, then you have this defense, which I'm not aware of a similar defense in Windows, and I think they need it. This is to prevent use after free and double free. When you're using the heap, which is different than the stack, you reserve space. I want 1,000 bytes on the heap. So you reserve it with alloc, then you use it. Then when you're done with it, you call free to free it, and then it can be reused. Well, it turns out that if you forget to free it, or if you free it, but you forget to destroy the pointers that pointed to it, you can still write to areas after they've been freed. And then you're writing data, and it's going to go into a different variable than the one that was intended. So you may have an ability to hack the app and get code execution. And another thing is double free. If you free an area of memory and then you try to free it again, it creates a write operation that you may end up controlling. So these are common mistakes, and this automatic reference counting is the simple solution. It just keeps track of how many times you've allocated something and how many times you've freed it, so you don't free it more times than you've allocated or less times than you've allocated it. This would help prevent these vulnerabilities. That's a pretty cool idea. All right, there are some heap defenses in Windows, but they're much more complicated. So all the apps are encrypted with digital right management. Of course, remember Apple, the App Store is highly commercially valuable. Most people make a ton of money selling iPhone apps, so you can't just copy those things and use them freely. This is that's what happens in Android. And so they're encrypted. They have digital rights management, and they're decrypted by the loader. So if you want to decrypt it with a debugger, you can run the app and use GDB attached to connect to the running image in memory, which is of course decrypted. And you find the base address and retrieve the memory section, and then you write it over the original encrypted section with DD. So you could create an unencrypted version. And you can do the same thing for Windows apps with Lord PE. we do it in 127. So here's the tools that help automate that process. And here's some more tools. Class dump Z and class dump are tools that will dump not the entire code of the app, but all the methods that are created. This gives you a list of the features. So here's a dump of the Starbucks app. Let me try and make it big. Let's see, it's this. Yeah, that's putting it in the wrong screen. Anyway, I'll leave it here. So this just shows what you get from a class dump. You don't get the full code. What you get are all the names of variables and routines that are used. So it helps you sort of map out the structure of an app. It helps, but if you want to really know what's going on in the app, this gives you the named items. So you can get some clue what area might be interesting. And then when you want the interesting area, you need a real debugger like Hopper. And Hopper will take you right down to the assembly code so you can read the assembly code. And this is ARM assembly code. So it's pretty tough. And we go a little bit towards this in the projects. I think Ghidra will be a lot better than Hopper. And we may get to that in this class, but so far I've been very distracted by COBOL, so I may not get to writing Ghidra projects to use on iOS apps this semester. Anyway, now we got some Cahoots. Let me move this out of the way if I can get it to, come on. There we go. All right, and back here I can get to Cahoots. All right. This is 128, chapter 2B. There we are. Okay. All right, I'm going to get my scores. Up here. Okay, good. Or 22. All right. All right. I'm expecting a few. We got 9 people. Maybe we're only going to have 4. I'll give it another 10 seconds. 4. All right. Looks like nobody else is coming. We will charge ahead with 4. All right. Which key does Touch ID control? It's the wrapping key that goes around the passcode key. So when you touch it, it can recover the key that came from the passcode. All right, what's the binary file format for iOS? Mako, that's it. That's the binary format. All right. What key is embedded in the hardware crypto accelerator? That's the UID. That is the identifier of your hardware. All right. And what feature mitigates heap corruption vulnerabilities? ARC, automatic reference counting, to prevent you from freeing twice, and other vulnerabilities like that. So it's Ken. And AT will have to tell me who they are if they want their points. Computer T. All right. So send me a text message if you want your points, AT. Unless my long-suffering grader can figure out who you are, which, oh, good, thank you. I got your name, good. All right, good. So now I know who you folks are. All right, so I'm gonna stop the recording.